answers for your homework, remember, please do them on a separate sheet. So don't just write it on the sheet that I give you out. Also, when you do your homework, I would look at it as soon as you can. Read over the problems, make sure you understand how to do them ahead of time. If you don't, that's an indication you might want to ask me questions about it. One thing I would encourage you to do is do not Google the answers. Okay? Actually try to do the problems. Guess what? You're not going to have Google on the exams. Okay? The whole point of homework is to get you ready for the exams. If all you're doing is Googling them to try to earn points, that's not going to help. Okay? The important part is that you're understanding what you know and what you don't know so that you get it ready for the exams. Okay? So please don't Google. Oh my gosh, please don't Google. Look at the problems, try them, struggle with them, ask me questions, but for the love of God, don't Google the answers. Okay? They're all out there. I promise you, all the answers for anything that you're going to be assigned out there on the internet. Guaranteed, 100%, you're going to find them. But it's not going to help you on the exams. Okay? So please actually try. But again, even if you don't start your homework right away, take 5 minutes, read through the problem, say, hey, I know how to start that one, I'm good. That one, you know what, I may have to think about that one, I might want to ask a question, maybe you try that one first. Okay, when you actually do have time to go do your homework. I'm not saying do it right away, right after class, start working on it right away, but take 5 minutes and read it. Okay, that's why I give you multiple days to do it. Because if you're starting at Sunday night and you have questions, then when it's due on Monday, if you're starting at Sunday night, you're not going to have time to ask me questions, right? Okay. So anyway, just wanted to mention that. All right. So we've talked about last time about how we actually do matrix addition, matrix subtraction, matrix scalar multiplication, matrix and matrix multiplication themselves. So today we're going to talk about properties of these things, how we might prove some properties of these things as well. So basically we're just going to write some things down today, do some proofy types of things today, if you will, going forward. So when we're talking about addition and scalar multiplication, we already saw that it behaves pretty nicely. So the properties that we're going to write down are not going to be anything that's earth-shattering. But to start this, let's make sure that, remember, if we're going to add matrices or subtract matrices, they better all have the same dimensions. So let's just start off with saying that they're all m by n matrices. And let's let, the book uses little c and little d as scalars. For our purposes, that's an ugly looking element symbol. For our purposes, our scalars will be real numbers. Most everything we will do this semester will be real numbers. But know that your scalars really can come from any structure that we refer to as a field. And a field just means that you can divide by anything but zero as far as the numbers go. So complex numbers are form a field. Rational numbers form a field. There are other examples of fields, but generally speaking, we'll talk about real numbers, but we can generalize this a little bit more if we wanted to. When I use that little, you're probably familiar with the notation, but just to make sure that we're all on the same page, this is just representing a set of all real numbers. This just means that it's an element of that set, right? So again, I'm assuming that you're probably already familiar with this. Declan? Yep. You're probably already familiar with the notation, but I just want to make sure that we're all on the same page with that. All right. So some of the properties, like I said, for addition and scalar multiplication, you're probably not going to find too earth-shattering. The first one is just that matrix addition is commutative. I really can add in either order. If you were going to prove something like this, you would want to show that the elements of the matrix that's formed by adding A and B together are the same as the entries, I should say. The entries that are formed by adding A and B together are the same as the entries that you get when you add B and A together in that order. Okay. So to show you how, just a starter proof, if you will, to show how that would work, this is how I would typically approach it. Let's define what we're going to use for our matrices here. Talk about their general entries. We talked about that notation last time. Well, we can refer to a matrix by its general entries. Again, if I want to show that these two things are equal, I need to show that they have the same general entry. So let's talk about how the definition works for addition. I'm using C and D for scalar entries, so let's use, I'm going to use F. E sub ij will be a special notation we'll use later on when we talk about a special matrix. So I'm going to skip the letter E for that. Let's call it F sub ij. How do we define addition? What does it mean to add A and B together? What do we do? How do we add these two matrices together?
A sub ij plus B sub ij.
Good. Exactly right. We just take the corresponding entries and add them together, right? So I would say, it's exactly what I would say. I would just write it as where F of sub ij equals A sub ij plus B sub ij. Now notice that I've written my general entry here in terms of the general entries of my two matrices that I'm operating together. So I'll stop there and I'll do the other side of the equation. If I do B sub ij, or excuse me, B plus A, and give it a general entry name, how do we define that general entry? What does G sub ij have to equal to? Yeah, it's just the other order, the other way around, right? Okay. So again, if I want to show these two matrices are equal, I need to show that their general entries are equal, right? Well, they have equal entries. And this is why I was mentioning that we've got all of our entries here are coming from the real numbers. What do you know about real number addition? What do you know about real number addition? What can you do? It's commutative, right? I can flip it around, right? So it doesn't matter. So now our G sub ij, I'll just go the other way. I probably could have started with F. It doesn't really matter. And I erased part of my word up here. We know that we can flip addition around for real numbers, but when we flip it around, we get A sub ij plus B sub ij, and that's exactly what F sub ij is equal to. And this is exactly what we wanted to show, right? They have the same general entry, right? Okay. So we can conclude that we really do have commutativity for addition here. We'll do a couple more of these as we go along, but I wanted to do this one because it's a pretty short proof to show that it really does hold. All right. So let's list out a few other properties that we have. Again, since matrix addition really just is adding real numbers together multiple times, but in the corresponding entries, we would expect that we would get similar properties for matrix addition that we do for real number addition. We had commutativity in the first one. This one's called what? Associativity, right? Again, if you wanted to do the proof, I'd write a general entry for A, general entry for B, general entry for C, and break it down like we did here. Notice we kind of did a meet in the middle approach, right? I got this general entry in terms of the things that I was adding on the left-hand side. I got this general entry in terms of the thing I was adding on the right-hand side, and showed that it had to be the same. And that'll be our basic approach for any of these. Yes. Those are the hypotheses that we're having. So I'm saying that, oh, sorry. I wrote it twice, sorry. I just wanted to say they have the same dimensions. I wrote the same word twice, sorry. That's my bad. I just wanted to say that they had the same size. I was thinking ahead and wrote the wrong word. All right. So these are kind of basic addition properties. So let's do some with the scalar multiplication, and in particular how it behaves with regard to behaves with respect to addition as well. This one looks like an associativity property as well. Oops. So if I take the scalar D and multiply it by the A, and then take that matrix and multiply it by the C, that's the same thing as taking the two scalars together, multiplying them first, and then multiplying it by A. It's an associativity property, but notice that this really is saying something, and we're going to talk about this later on when we start talking about vector spaces. These are two different types of multiplication. This object is a number, this object is a matrix, right? So this is scalar multiplication. And then I end up with a matrix and multiply by another scalar. Okay? So those both are scalar multiplication, a matrix with a number. What kind of multiplication is right here in the parentheses? They're two numbers. It's just multiplying two real numbers together. That's a different type of multiplication. Okay? Okay? So there really is something, even though it's hopefully fairly obvious what's going on, there really is something there. It's different types of multiplication, right? In the first case, you have matrix times a number. That's two numbers, right? Regular old multiplication. Okay? Something's going on there. And like I said, we're going to expand on that later on when we talk about vector spaces, but I want to mention that. Okay. All right. What else do we have? Well, there's a special scalar 1. This one's hopefully pretty obvious. If I take 1 times any matrix, I should get that matrix back again. It's an identity type of property. Not a lot of theory going into that. It's, again, something that is going to pop up later when we talk about vector spaces. There's a reason why we call it scalar multiplication. If you think about vectors, when you multiply a vector by a scalar, what does it do to the length? So if I take a vector times 2, for those of you that have done with vectors. Take a vector times 2, what does it do to the length of the vector? It makes it 2 times longer, right? Okay. Same idea. That's why we call it scalar multiplication. It changes the scale. Well, what number would you want to multiply by and not change the scale? 1. That's what that's saying, right? That's why that's in there, is that if I want something to be nice and behave with vectors, I would assume that if I take the number 1 and multiply by the vector, it shouldn't change that vector at all. It should keep it the same. Like I said, not exceptionally exciting, because what am I going to do with this 1? I'm going to take 1 and multiply by every single entry. It's not going to change any of the entries. Okay. So it's not in here because it's such an exciting property. It's leading into vector space stuff later. Okay. All right. What other properties? Well, I said something about the fact that the next couple of properties here should be, how does scalar multiplication behave with respect to addition? There's a couple of those. Oops, forgot to distribute. The first one here says that scalar multiplication distributes over matrix sums, right? But it also works the other way around. The next one says that scalar multiplication also distributes over real number sums. And again, these are not surprising properties, but you should think about what it really is saying. The objects we're adding together here are what? Matrices. The objects you're adding to here are not real numbers, right? But notice that this property says we're changing a real number addition to what kind of addition? Matrix, right? There's something going on, right? It's changing where that addition lives. Let's do one of these as a proof just to kind of go through that as well. I'll do the last one because it looks like I have a little bit more space. All right. So notice that we have one single matrix that we're doing here. So let's let A be the matrix A sub ij. Then, pardon me, if I do C plus D times A, and I get a general entry here, how do I get the general entry of taking this scalar C plus D and multiplying it by the A? How do I get the general entry? What do I do?
C plus D times A sub ij.
Good. I take the C plus D times A sub ij. And again, notice I have this general entry written in terms of the general entry of the matrix that I'm dealing with. So I'll stop there and I'll work on the other side of the equation. Okay. Notice on the other side of the equation I have two matrices to deal with. I've got C times A. What does G sub ij equal in that case? Good. The C times the A sub ij. If I do the same thing with D times A, oops. What does D times? What does dA equal? What does the H sub ij equal? Good. D times A sub ij. Good. Now, what do I want to do with the C times A and the D times A on the right hand side? Add them, right? So let's do that together. Again, I'll give it a different name. You need to go down the alphabet a little bit because I don't want to use I or J since I'm using those for subscripts. Next letter I run across is K. What's your K sub ij equal to? Good. Gij plus hij. And if we substitute, G sub ij is good. C times A of ij, A sub ij, and H is equal to, oops. Good. I know, lots of stuff, but let's see if we can keep track of where we're trying to get to. I'm trying to show that these two things are equal to each other. What did we call the general entry of the left-hand side? What letter did we call the general entry for this one? That was F, right? This one, what letter did we use? That was the K, right? So at the very end here, we want to show that the F ij is equal to the K ij, right? So let's do that. K sub ij, we just said is C sub A, or C times A sub ij plus D times A sub ij. These are just now real numbers. What can I do with the A sub ij? Factor it out. Oops. All right. And do we recognize what that's equal to? The F. Good. And that's what we wanted to show. So we're done. So again, this is generally true for any time you want to show that two matrices are equal to each other. You need to show their general entries are equal. That's how we show that two matrices are equal. So this is the technique that we'll do anytime that we are trying to prove a property of matrix arithmetic. We'll do one here in a minute with matrix multiplication as well. But are there any questions about that particular proof? You can probably write it a little shorter, but I think it's more instructive if we just label a general entry and show what that general entry has to equal and just keep working through it. All right. One of the reasons why they're doing all these, some of these properties is just to try to introduce us to stuff with a vector space stuff later on in a couple of chapters down the road. So one of those things is the idea of talking about additive identity. Remember, anytime we talk about an identity, we mean an element that you can operate with anything and you just end up with that second thing again, right? So if I want to do additive identity for real numbers, what do you add? And it doesn't change the real number that you're adding to. What do you add? 0, right? So if I want to do the additive identity for matrices, what do you think I want every single entry to equal? 0, right? But notice that you have to change the size for all of them, right? Because I need to make sure that I have same sizes when we add, correct? Okay. So when we do the additive identity, we write it as an m by n matrix will have a different additive identity for every single size. And in this case, I'll write it, rather than general entries, I'll just think about it as a rectangular array. Every single entry is 0. So every single entry is 0 in the matrix. Which makes sense, right? Because again, the way we define matrix addition is entry-wise, right? Or if you like to think about vectors, it's kind of component-wise, right? Take your 1, 1 entries, add them together. Take your 1, 2 entries, add them together, and so on down the line. If I don't want the matrix to change when I add it, I need to add 0 every single time. Okay. So that's what we mean by the additive identity. And the properties of the additive identity are the same as what you would expect for any additive identity. If I take a matrix and add the 0 matrix, which you typically use as an O, and as long as we understand that we need to have the same dimensions, I'm not going to write that sub mn every single time. Okay. What do you get when you add the additive identity here? You get A back again. Good. Now, notice that this really does have its roots in trying to solve equations, right? Remember that, for example, I'm going to write it on the board rather than on the screen because I don't really care if you write it down or not. If I try to solve for x, what do I need to do? Subtract 3, or said another way, I need to add the additive inverse, right? That way. But notice that when I add the -3, I'm really adding it to this number, so I have to reassociate first. Right? And then this thing really technically is 0 on this side, right? Okay. So notice there's a couple of different things I need to know here. Number one, I need to know that additive inverses exist. And I need to make sure that when I add 0, I don't change anything, right? Now, obviously, you're not going to do all this work when you're doing that equation, right? But that's what goes into it. This is why we care about additive identity ideas, is to have its roots, is all of it, like I said, has its roots in solving equations. I need to get know that if I get back to 0, I don't change the number. Along those same lines, oops, if I take A and add negative A, I get back to the 0 matrix, which is kind of the same idea we did here, right? The whole reason why we added negative 3 was to get 0. Same concept. The last one is a special property that doesn't always hold for particular structures. It does hold when you're doing scalar multiplications. That's the number 0. I'll try to write it a little skinnier. Try to make the sizes different. This goes back to that kind of that 0 factor property you've used in algebra class before. If you have a product that equals 0, then one of the factors has to be 0. That's basically the same kind of thing here. Notice that one of your objects here is a scalar and the other is a matrix. Yes.
Why didn't you say and or? I mean, they could both be 0.
Yeah, when we do or, we always assume it means inclusive, so the and is included. Yeah. You're right. It is and or. They could both be 0. Absolutely. Yeah, one or the other, or both have to be 0. Lost my train of thought. Sorry. Anyway, when you multiply these two things together, it looks like that 0 factor property. But notice one of these is a scalar and one's a matrix. Here in a minute, we'll do an example of matrix multiplication where the product can be 0, but neither matrix was 0 to start with. Okay. So this is a special property of this specific type of multiplication. All right. In any event, let's go and move on to matrix multiplication. All right. So remember, matrix multiplication was a little bit strange in the fact that we had to take rows and match them up with columns, right? And do kind of a dot product idea. If you've seen dot products before, right? All right. So first thing we notice as an example, if I take, let's just do two 2x2 matrices here and reverse the order. Let's say I had 1, 3, negative 1, 2, and multiply it by 1, 1, 2, negative 1. Say, what do you get when you multiply those two things together? What do you get in the upper left-hand corner?
4. Upper left.
7, right? Upper left-hand corner is 7, isn't it? 1 times 1 plus 3 times 2, I get 7. Okay, what do we get in the upper right-hand corner? Yep, negative 2, good. 1 times 1 plus 3 times negative 1. Lower left is 3, and lower right is negative 3. Yeah, good. We see where the numbers are coming from? Okay. Eventually. What happens if we flip it around? What do you get in the upper left-hand corner now? I got a 0. So we'll do the next 3 is we'll do the other 3 entries, but right away, are these two answers going to be the same? No. So matrix multiplication is not commutative, right? In fact, not only do you not necessarily get the same answers when they have the same size, it's possible when you do matrix multiplication that one of them is defined and the other isn't, based on the way we have to have the number of columns in the left matrix has to equal the number of the rows of the right matrix, right? But generally speaking, even if you can multiply both directions, you're not going to get the same answer. Sometimes you can, but generally speaking, you don't. Okay? Do the other ones. What's the upper right? The 1, 2 entry, 5. The 2, 1 entry, 3. And the 2, 2 entry, 4. Okay. And again, just to emphasize, those are not equal to each other. This is not commutative, generally speaking. Like I said, even if you have the same size square matrices where you can flip them around, you don't necessarily get the same answer. Sometimes you do, but most times you don't. All right. However, there are some properties that do work. Associativity works. You can regroup. Distributivity works. But since it's not commutative, I also need to check distributivity on the right-hand side. What would you get on the right? If you know that it distributes, what would the answer be when you distribute the A through? BA plus CA, making sure that we keep them on the same side. Okay. This is not necessarily AB plus AC. It's distributing on the right. You're multiplying it on the right. Everything needs to stay on the right. Okay. And then the last one is that associativity with a scalar. Basically, it says that I can put the scalar, I can do the matrix multiplications together, then multiply by the scalar, or I could take the scalar times the A and then multiply by the B. Or if you want to be fancy, I can take the scalar with the B first and then multiply by the A. I can move the scalar wherever I like. Notice in particular, this is telling me that I can basically do my scalar multiplication on either side. I get some commutativity with scalar multiplication, but not with matrix multiplication. Yes? Say that again? Yeah, I could. No, not. It's not a distributive property. It's multiplication, so I have to multiply by one of them and then do my other matrix. I wouldn't multiply by both of them. That would be like the same idea here. Basically, you're just saying if I have 2 times maybe 3 times 4, then it doesn't really matter which one I do. I could do the 2 times the 3 and then multiply by the 4. Or I could move the 2 over and multiply it by the 4 and then multiply by the 3. But again, I wouldn't take the 2 times the 3 and the 2 times the 4. Yeah. All right. So let's do one of these with a proof. I'll do the second one here because you'll notice that the third one I asked you to do on the homework. Okay. All right. So let's make sure that we can actually multiply everything together and be able to add. What has to be true about B and C here if I'm going to be able to add them? Same dimensions. What has to be true about the A then and the B and the C? Yeah, the columns of A has to be the same as the rows of B and C, right? So to start this off, let's say I say let A be an M by P. And I'm going to do a little shortcut to just do my subscript down here to define my dimensions so I don't have to write it all out. Let's let B be B sub ij, where I have P by N, and then C also be P by N. I'm only putting the subscripts in there because since I know they could have different dimensions, I'm going to make sure that I label what the dimensions have to be. In particular, that I have to make the columns of my A be the rows of my B and my C. Right? On the left-hand side, we're going to add B and C together. When we add B and C together, what does the general entry have to look like? Good. All right, so now let's think about how we get the general entry of this product. So remember, we have to run across the row of A and down the column of B, or well, the second matrix, or the B plus C in this case, right? Okay. And then add those up, correct? So remember, I mentioned this the other day. Running across the column and down the row, I start in the first one, either one, right? I start first column or first row, depending on what I'm talking about, and continue all the way until I get to the p column or row, depending on which one I'm talking about, right? I run across the columns of A and down the rows of B plus C. So I have AIK DKJ, right? We go across the columns. So my column number changes for A. I run down the rows for the B plus C. That's how we define it, right? Okay. If you need to write it out, let's just say if you had the first row, that would be, say, the first row of A and the first column of the other matrix. Notice when you multiply, what subscript changes? The second subscript changes for the first matrix. The first subscript changes for the second matrix. Right? Indexing across those things. Okay. In the previous statement, what was D sub ij equal to? It was bij plus cij, right? So what's D sub kj equal to? If it's Dij, it's Bij Cij. So what's Dkj equal to? Good. We're just replacing the I with the K, right? So it'll be Bkj, Ckj. All right, so now we have the left-hand side written in terms of the general entries of the individual pieces, right? So let's stop there and do the other side. B and C, yep. Okay. All right, so let's do the other side. I need to do AB, I need to do AC, I need to add them together, right? Okay, so next letter, let's use G. Again, this is a product. When we do a product, the general entry is a sum of things. What are we going to multiply together on the inside here? Good. We're going to run across the columns of A and down the rows of B in this case, right? Because we're doing A times B. So if we do the same thing for A times C, what's that entry going to look like? Good. It looks almost exactly the same. The only thing is that we're multiplying by the C's instead of the B's, right? Oops, that's a K. What do we want to do with A, B, and AC? Add them? I'm using K as my index, so I don't want to use K as a general entry. L is always problematic because L's can look like ones, so I'll go to M for the next letter. What does M sub ij equal? Good. Gij plus hij, right? That's how we add the two matrices together, those general entries. We have things that we can substitute in for Gij and hij, right? Our G is this sum, and our H is this sum. No, it's not. It's a C. Again, we worked with the right-hand side. I now have my right-hand side's general entry in terms of the general entry of the three matrices. Now let's see if we can get them to be the same, right? All right, so our M is that sum of sums, right? For lack of a better term. How can I rewrite this? Well, notice all this is saying is add these things together over the same index, add these things together over the same index. How can I rewrite that? Can I write it as a single summation? Yeah, I can write this as AIKBKJ plus AIKCKJ. Just combine them. That's just a bunch of commutative properties of addition going on. Do you see anything that you can do now inside the parentheses? Good. I can factor out an AIK. And do we see anything that's equal to? That's the F's, right? Which is what we wanted, isn't it? I wanted to show the M and the F's were equal to each other. So we're done. I know, not the most fun thing in the world. No. Unfortunately, there's not really. Again, because to prove these properties of arithmetic, we have to show the general entries are equal. So that's about the best way we got. I know, there's a lot in there, but you should be able to follow this particular proof to be able to do the one that's on the homework. Okay. This is why I said you might want to also want to look at it ahead of time rather than wait till the last minute to try to do it if you've got questions. All right. So we got all those properties written down. We'll talk about some more of these properties next time. In particular, we'll talk about another special matrix. We talked about the additive identity. We'll talk about multiplicative identity next time. And then we'll talk about how we also do transposes of a matrix and talk about some properties of that. So we'll do that next time. Have a good one. We'll see you on Friday. What's that? You'll have to do something like this on the test, yes. Yep. Okay.